Dear colleagues, it's my unbelievable pleasure to start this section devoted to Canadian Journal of Statistics Award. And I'm very happy to present here the talk by Cong Jiang, Michael Wallace, and Mary Thompson, entitled Dynamic Treatment of Regimes. So that will be a very dynamic talk. Yes, and Cong, the floor is yours.
Okay, thank you. Thank you. Thanks, everyone. It's my honor to to give the presentation for this paper, and our heartfelt thanks to go to the committee SSC CJS award and for this recognition. And my presentation, the title is the Dynamic Treatment Regime. So first, I will give you a brief introduction about the dynamic treatment regimes, interference, and the motivation examples regarding the smoking cessations in the household. And later, I will briefly introduce the optimal DTR estimation for the optimal treatment, sequential optimal treatment, and the particular method we are focused on in this paper. And later, we will explore how to integrate the interference in the method that we care about. Finally, I will show you some simulation studies in this paper, and we will see some results from real-world application from the population assessment and tobacco usage, the PATH study. Okay, the precision medicine or personalized medicine refers to the principle of the tailoring treatment to the individual patient characteristics. Rather than give all the patients with a particular disease the same drug, we instead consider which treatment is the best for each individual. So we have the slogan that the right treatment for the right patient at the right time. So this approach is formalized by dynamic treatment regimes, the DTRs. So in the context of the multi-stage treatment decisions, dynamic treatment regime are the sequence of the decision rules which at each stage takes the patient's information as input and then output the treatment recommendations. So in our real-world application in the smoking cessation studies, a simple DTR could be if a smoker has a plan to quit. That's the information we get from the patient. The treatment recommendation is give the nicotine replacement therapy. Otherwise, give the e-cigarettes, such as vaping. So our goal is to use the observed data to estimate the optimal DTRs, which are the sequence of the treatment rules that maximize or optimize the expected clinical outcome across all the patients. So here is a simple causal diagram in the single decision point. So we have the X, which is pre-treatment covariance. And we have the treatment E here. We only consider binary treatments coded as 0 or 1. 0 could be the standard care or placebo. Treatment is A equal 1. And for the outcome here, we consider continuous outcome. And we assume that the larger value of Y is preferred. So for the interference, as in the wider causal inference literature, DTR assumption relies upon the assumption of the no interference. That means your outcome will be affected about your neighbors. So although this assumption is reasonable, this assumption can be violated in many situations, such as the infectious disease, vaccine effectiveness, and social network contact. So a little work has focused on the DTR estimation with the interference. So the paper or this project will focus on is the network interference. We suppose the individuals are in the networks. And a primary interest of individual is called an ego. And those to whom the ego is linked are the authors. You can see that in this simple network, the individual 1 is an individual of primary interest. And we consider only the first order neighbors will have the impact. Those first order neighbors treatment will affect the outcome of the individual 1. Okay, I think the version is a little bit different. So as an illustration, our motivating example is to study a real-world application in the smoking cessation studies. So a lot of the study has focused on the idea that the desire to quit smoking alone might not be sufficient motivation in itself. So some researchers address the smoking cessation in the couples of the families. So meanwhile, much literature suggests use the e-cigarettes as a smoking cessations to reduce the nicotine dependence or smoking. So here is the real-world application from the study of the population assessment of the tobacco and health, the PATH data. Launched in the 2011, the PATH study is the nationally representative longitudinal survey study about the tobacco usage and health. And it collects the data by the wells. And we consider first 4 wells to formulate as the 3-stage decision problems. And our goal is to use the PATH data to illustrate the DTI estimation method with interference to investigate smoking cessation strategies for reducing smoking dependence within the household. So here, our method is focused on the one area called the regression-based DTI estimation. Alternative way is called the classification-based DTI estimation. It's 2 different approaches, but here the focus is on the regression-based. So we assume that the expected outcome can be split as the 2 parts. The first part is the blue, the G function. We usually call the treatment-free part. That is the expected outcome on the no treatment. The second part is called the gamma part, the gamma function, usually called the blip function, which is the impact of the treatment on the outcome. And the covariance in the treatment-free part and the treatment part could be different, which are in the covariance X set. For example, we consider this simple linear model here for the smoking cessations. We consider outcome regression model. We have the main effect of the PQ. It means the plan to quit. And we have the main effect of the treatment A here with the parameter psi 0. And we have the interaction term between the treatment and plan to quit with the parameter psi 1. So the question is, what kind of individual treatment rule that we can learn from this linear model? So recall that the treatment-free part, the blue part, has no relationship with the treatment. So if we want to choose the optimal treatment, the only focus is on the gamma function. So if for the red psi part, the psi 0 plus psi 1 PQ is larger than 0, to maximize or optimize the outcome, we need to choose the treatment 1. Otherwise, we choose the treatment 0. Recall that our focus is on the binary treatment. Okay, so to tailor the treatment, the parameter in the gamma function, in the blip function, is all that I need to know to tailor the treatment. So that's a single-stage decision problem. So for the multi-stage decision problem, it is a little bit complicated because your current decision will affect both future decision and outcome. So in the treatment decisions, your current stage decision might not only affect the immediate outcome, but also affects future outcome. It's called the delayed effect of your treatment. So to make the correct optimal decision, our decision making should be far-sighted. We should consider longer for the decisions. So how does it work? So like many methods we use, like the Q-learning, originally from the reinforcement learning literature, they use the backward reduction to solve these sequential decision problems, break it into a single-stage decision problems. Now let's consider this simple example with two-stage decisions. So first, let's consider the last stage. That's the stage 2 in this example. We have all the history information denoted as H2 here. We have the previous covariance, X1 and X2. And we have a previous treatment, A1 here. And we solve the problem from the last stage. And we do the one-stage implementation. We can find the A2 optimal that maximizes the final outcome Y. Once we have this A2 optimal, we can construct a new outcome that is denoted as Y2 optimal here. The Y2 optimal, this is the potential outcome if the second stage is optimal. So once we have this new outcome, we can do the one-stage implementation again. We can find the A1 optimal. So finally, we will find the sequence of treatments A1 optimal and A2 optimal that maximize the final outcomes. Okay, so we know that the multi-stage decision problem a little bit complicated, but backward induction can help us to reduce the multi-stage decision problems into a one-stage decision problem. The key point is that we construct this new outcome. Here we also call the pseudo outcome, which represents the potential outcome if the future decisions are made optimally. So in the regression-based DTR estimation, we also have a lot of methods are available. So we have the Q-learning and G-estimation. So for the Q-learning, it's easy to implement, but it lacks of the robustness. The G-estimation was proposed by James Rubin. It has a nice property called the double robustness. I will give more detail about this property later. The method that we are focused on in this paper is called the DeWolf, the dynamic weighted ordinary least square, was proposed by Wallace and Moody in their 2015 biometrics paper. So DeWolf combines the strengths or advantages from both Q-learning and G-estimation. DeWolf is easy to be implemented. So for each state, it is just the weighted ordinary least square. It's also easy to explain to the physicians. Or importantly, the DeWolf have the double robustness properties. Now let's dive into this method. So again, our outcome model have two parts, treatment-free and blip part. The DeWolf is applied by specifying the three models. The first is the treatment-free model. It's for the treatment-free functions. It can be any functions. And model is to model this function. And the blip model is the model for the blip functions. And here we assume that the truth for the blip model is linearly modeled with the parameter psi. And finally, that's the treatment model. That's expectation of the treatment. So when the treatment is a binary treatment, it is the probability of receiving this treatment given your covariance. That's usually called the propensity score model in the causal inference literature. So the DeWolf estimates the psi. The parameter psi is all we care about for Taylor treatment. The DeWolf estimates psi while weighted ordinary least square of the outcome or the covariance in treatment-free and blip models with the width W here. That's width is absolute value width. That's the distance between the observed treatment minus the propensity, the probability that you receive in that treatment. So the Wallace and Moody, they give the width criteria. not the only one WES we can use. Any WES satisfies this WES criteria will guarantee the divorce double robustness. So regarding the double robustness property, that is, we can get the consistent estimator for the tolerant parameter psi in the blip function if either treatment model and or treatment-free model is correctly specified. So having seen the whole framework for the divorce, now let's explore how to integrate the interference or network interference into the divorce estimation framework. First, we consider interference terms. So we denote A curly N here. That's the treatment vector of the individuals in the neighbors. And the network interference is a mapping function. It's a function T that maps this treatment vector to a scalar. So that's essentially the summary of your treatment, the treatment of your neighbors. So for example, the interference term for the mapping function, T could be the number of the treated neighbors. It can be expressed in this form with the capital N here denotes adjacency matrix. And this mapping function could simply be an indicator function, which indicates the existence of the treated neighbors. In addition, this mapping function can be a fraction of your treated neighbors. These interference terms are the summary of your treatment of your neighbors. So by setting the adjacency matrix, we can vet our neighbors by the strength of the relationship. For example, I could be more likely to be infected by my close friends than the other friends. So we can set this adjacency matrix. So in our real application case, that is the two-person household network. This vector is treatment vector, neighbors treatment vector is just a scalar. That is your spouse treatment. We denote as A superscript A alter here. So the interference terms are the same. For example, the number of the treated neighbors is same as the fraction of the treated neighbors. So once we have the concept of the interference term, now let's see how can we integrate this term into the divorce method. And we give the two modeling methods. The first one, we consider this interference term, and we assume that the blip function can be linearly modeled in this form. We have the original tolerant parameter xi, and we have the interference term T of an here. So for this interference term, we also assume that it is fixed and known and correctly specified in this blip model. For example, we can have this simple outcome model. We have the linear model for the treatment-free function, and we have the blip model, and we include the interference term in both models. So the following question is, how can we consistently estimate these tolerant parameters if we have this interference term in the blip function, in the blip model? So the idea is based on the propensity score. We give the new definition about the network propensity function. So the propensity score was proposed by Robinson and Rosenbell and Robinson in the 1983. That's the balancing score that balances the covariance between the treatment group and the control group. So we, based on this idea, we give the network propensity function. That's also the balancing score. We can balance the covariance. If in the presence of the interference, we can balance the individual's covariance among the treatment combinations. So we consider the neighborhood and each individual, the treatment is a combination. We can balance the covariance among these treatment combinations. That's the main idea for this, the network propensity function. So let's denotes Ni denotes the set of the neighbors of individual I, and sets the SIA denote the set of the treated neighbors. So the network propensity function, that's the joint probability function of the individual I receiving the treatment AI, and their neighbors, treated neighbors, are in this treatment set SIA here. So we have the further assumption that is conditional independent assumption. Conditional the covariance of that individual and the covariance of individual's neighbors, the treatment are independent. Then we simplify this joint probability as a product of the marginal probability. So essentially decomposed by the three parts under this conditional independent assumption. The first part is the propensity for the individual I. The second part is the propensity for the treated neighbors. And the third part is propensity for the untreated neighbors.
Go ahead.
Yeah, so that's the whole idea about this propensity, network propensity function, is to balance the covariance. So now, once we have this network propensity function, I will give you the first theorem in the paper about the balancing property with the network interference. It is related to the double robustness property of the divorce. So this theorem tells us that if the true outcome model have two parts, the first the treatment-free part, the second blip part, both of them have the summary of the neighbors treatments, that is interference term T of AN here, then both the standard divorce weights and the new proposed network weights will give the consistent estimator of the parameter psi. So for this new proposed network propensity weights criteria, that is in equation 1, that's the product of the network weights and the network weights network propensity function equal the constant given the individual's covariance and the covariance of the neighbors and degree of that individual. That's equal the constant. So any weights satisfy this network weights criteria will work. So we also show that this new weights criteria is sufficient but not necessary condition of the standard divorce weights criteria. It means that the proposed network weights will also satisfy the standard divorce weights criteria, but not the other way around. Okay, I will give you an example to demonstrate it. So, for example, we consider this simple outcome regression model, and we have the treatment-free part and the blip part. And the treatment rules from this model is indicator function for related to the blip function. So the double robustness of the divorce based on the previous theorem that we just saw tells us that if either treatment-free model and or treatment model is correctly specified, the tolerant parameter of the psi that can be consistently estimated by the outcome regression with the network propensity weights or the standard divorce weights. So here, the network propensity weights has two components. First is the weights for the individual I. The second is the weights for the neighbors. And this weights satisfies the weights criteria we just saw in this equation 1 here. The product of the weights and the proposed network propensity function equal constant. So next I will introduce the second theorem or second modeling framework. So patients give the treatment recommendation based on blip. Sometimes we also interested in the parameter of the beta 2. That's the coefficient of the summary of the neighbors treatment. So the question is, how can we also consistently estimate the beta 2 and the parameter psi? That's the following idea about the It's jointly decision making. We give the different modeling method. We consider the two parts. Recall that in the presence of interference, we not only consider direct effect from individuals themselves treatment, but also the spillover effect from neighbors treatment. So we model these two effects parts using the two different blip models. The first one is only related to the interference term with the parameter Kc, and with the covariance, the X Kc here. And the second one is what we just saw, is the blip psi part. We have the tolerant parameter psi and the interference term T with the parameter psi here. For example, we have this linear model. We have the first Kc blip function and the psi function. And our goal is to find the interference term and the treatment that simultaneously maximize these two blip functions. So the parameter Kc and parameter psi is all we care about for this maximization problem. The second theorem about the balancing property with the network interference, which is regarding the double robustness of the divorce, is as following. So this theorem tells us if the true outcome model it has the three parts. The first, the treatment-free. The second is the two blip model. The first is only related to the interference term T of An with the parameter Kc. The second one is the blip model with the parameter psi. And only the network weights, that is, satisfies the West criterion 2, essentially equals the equation 1, can give us the consistent estimate of both Kc and psi. So as an illustration, we have this outcome model, and the divorce double robustness property tells us that if either treatment-free model and treatment model is correctly specified, then the parameter Kc and the parameter psi can be consistently estimated by the outcome regression with this network propensity weights. So again, this network weights is in the absolute value weights form. Any weights satisfies the weights criteria. We are guaranteed this double robustness property. So we have seen the one-stage decision problem, the two modeling framework about the double robustness of the divorce. So our goal is to estimate the sequential treatment rules. Recall that the backward induction will help us reduce the sequence of the decision problem as the series of the one-stage decision problem. The key here is we constructed the pseudo outcomes, which we assume that the future decisions are optimal treated. Future decisions are optimal made. And our goal in this network interference is maximize the outcome of the eagles. So we try to find the sequence of the decision rules in order, output the treatment A1 optimal, A2 optimal for the eagle that maximize the final outcome Y eagle. So we solve the problem from the last stage. For the final stage, the observed outcome is that pseudo outcome. And for the previous stage, we construct this Y tilde here as the pseudo outcome. This pseudo outcome is constructed by the AK optimal here. That's optimal treatment rules that we learn from our model. Okay. So that's the theory part about the double robustness of the divorce when we consider interference. We have the two different modeling methods, and we can guarantee the double robustness when we use the network weights based on the network propensity functions. So in the following part, I will show some simulation studies in this paper. So our goal here is to investigate the impact of the interference and demonstrate the use of the both standard and network weighted ordinary least square. So we consider single-stage decision problem and the multi-stage decision problem. So in the single-stage decision problem, we start from our real data application, which is the form of the network of the couples. We have the 3 sub-studies, and later we consider broad network scenarios, and we study the 5 types of the fixed networks. And the first 2 are simple ones. The first one is the ring consisting of the points on the circle. The second one is the square lattice. 3 and 4 are very famous network realization from the ER model and from the BA model. And last one is about spatial data. It's from the long-leaf pine tree data set. For the multi-stage decision problem, firstly, we also start from the network of the couples, and then we consider the network realization from the spatial data. So that's the causal diagram that we relied on in the studies in this single-stage decision problem. For the left-hand side, we just consider couple networks. Right-hand side, you can see that curly N here represents the network. We consider your neighbor's treatment can affect your outcome, and potentially your neighbor's covariance can also affect your outcome. So that's the data generating process for the study 1A. Here for the treatment, we have the covariance X and the nonlinear part for the covariance sin X here. And for the outcome model, the treatment-free part, you can see here have nonlinear functions of log function and X power to 3. And also we have the blip part. So that's corresponding the theorem 1. Our goal is to estimate in the blip function, blip parameter, the psi 0 to psi 3. So to verify the double robustness, we have the 4 scenarios to consider. The first scenario is both treatment-free model and treatment model are misspecified. Scenario B and C is one of the model is correctly specified. Scenario D is both of these 2 models are correctly specified. So if we misspecify the model, we omit the nonlinear terms. We just consider linear term in our model. Okay. So that's the setting for the study 1A here. As I said, we have nonlinear terms in the treatment-free function. And for the method, we consider 3 methods. The first one is we analyze it as if we don't know about the interference. The second one is we consider the neighbor's treatment in the model, and we'll also still use the standard divorce width. And third one is to consider our proposed network width. So in this, the 2 people in the household, the network width is the product for that individual and your author's width. It's the product of these 2 widths. So this is a table about the result. So you can see that here the column A, B, C, D corresponds to these 2 different misspecification scenarios, and the method 1, 2, and 3 here corresponds to the 3 methods we just saw. So these numbers are called the mean optimal treatment rate. That's the average proportion of the patients for whom their recommended treatments align with the treatments that are truly optimal. Okay, the recommended treatment are from the model that we learned. So this graph, we can see that this rate for the method 1, that is, we omit the interference, is very low, very poor. And this figure demonstrates double robustness. For the top row here is from method 2, and the bottom row here is method 3. And in each plot, we have the A, B, C, D, the misspecification scenario. So for the scenario A, both models are incorrectly specified. It has a bias for the tolerant parameters. That's just the example for the study 1A. And here I give the summary about our simulation studies. So when the analysis does not account for the interference, that is method 1, we are considering the rate at which the recommended treatment align with those that are truly optimal are poor. However, the both proposed method demonstrates the marked improvements. So secondly, for the both standard DeWatt and the DeWatt with the proposed network Wallace demonstrates the expected double robustness. Finally, for the network Wallace also provides the consistent estimator for both parameter psi and parameter xi. That corresponds to the second theorem in the paper. So let's go to the next part about the real-world application. So our goal is to use the past data to illustrate the DeWatt extension with the proposed network weights and to investigate the DTR strategies or treatment rules for reducing the smoking within the household. So we have a lot of the variables in each wave. So for example, we have the demographic variables, the smoking variables, e-cigarettes variables such as e-cigarettes use. That's the treatment we're considering, and the predictions of the cessations and the cigarettes-dependent related variable. So that's the outcome, the continuous outcome that we construct based on the previous studies. We can, based on the question, we can give the score to score this cigarettes dependence. So that's the causal diagram. The thing I want to highlight that is in the study of the tobacco usage or the e-cigarettes, I know much literature focuses on the idea to study the effects of the e-cigarettes. They try to use the causal inference method to estimate the effect. I found that the use the causal diagram, which applies some assumptions, but it's very helpful for us to identify these causal problems. Actually, for the variable selections, it tells us not every variable should be considered. I mean, in this causal diagram, for example, this collider. The collider is the cigarettes dependence, which is your treatment and your outcome both affect these colliders. So in some causal literature, if we conditional or adjust this kind of the collider variables, we will have some bias in our models. So I want to say that when we consider real-world applications for every variables, we combine the domain knowledge and the existing literature. We find the very details about how to select this covariance in the study. Also, in particular for the tolerant variables. And we finally select the the age and the plan to quit as the tolerant variables. So we also have the 3 methods to investigate this smoking cessation. The first method is a naive analysis. We omit the neighbor's treatment. The second method is the standard DeWatt Wallace. We include the alters. We include alter as the one term in the blip model and the treatment-free model. But this method uses the standard DeWatt Wallace. And finally, as the simulation demonstrated, we use the network Wallace in our model 3 here. Okay, so that's the result of from the 3-stage decision problems. So we have the 4 waves. We formalized as the 3-stage decision problems. That's the result from the blip model for the parameter psi and parameter xi. So we consider 2 different scenarios. One is your alters treatment is predetermined. And we consider this as information for your treatment decisions. Then you make the decision for the ego. The second scenario is your alter is not predetermined. We can find the optimal rule for the both individuals in the household. So I will give you an example. First, for the aorta, your neighbor's treatment is predetermined. For the last stage, we can see here, if the aorta equal 1, it means your spouse is use the e-cigarettes. And you have the plan to quit. The treatment recommendation is use the e-cigarettes. And if your spouse is using the e-cigarettes, but you don't have the plan to quit, if your age is larger than 35, and the recommendation is use the e-cigarettes, okay? And for the second scenario, we can use that the parameter C to simultaneously make the recommendation to the ego and alter. So here for the last stage, for the alter is to use the e-cigarette, and for the ego here, if you have the plan to quit and your age is larger than 35, is to use the e-cigarette. That's the treatment recommendation from this analysis. So to compare the different methods, we also consider the so-called value function. Here, the value functions of the three methods to determine their effectiveness in reducing the cigarette dependence. So the result and the conclusion here is the method 3 using our proposed network that provides the highest average values, indicating the most significant decrease in the cigarette dependence. So during the whole process, you can hear that we have a lot of assumptions. This is a project that I want to focus more on this DTR estimation and interference. So in my research proposal, that's a big part of my research proposal. And so we also have the work just be published to consider discrete outcomes as a smoking cessation for each individual, and we make the decisions for this household. And also, you know that now I'm the postdoc at the University of Montreal with Mireille Schnitzer and Denis Thielbault. We focus on the vaccine effectiveness studies. So that's also an extension about this work to consider individual treatment rules and also consider interference simultaneously. For example, we try to estimate heterogeneity of the COVID vaccine effectiveness. And the question is, how can we construct the optimal vaccine allocation strategies, consider the limited number of available doses? Also, in the presence of interference, a little bit complicated, right? We also consider a question like how to estimate the direct effect and spillover effects within the framework of the different sampling strategies, and what are the corresponding optimal vaccine allocation strategies. So finally, I want to thank the support from the Department of Statistics and Actuary Science of the University of Waterloo, and also thank the support from the OICR, which also give me the scholarship during my PhD time, and also the support from the CIHR. With that, I thank you for your attention.
Thank you very much for so exciting talk here. So now here, questions, comments, remarks, suggestions. Please, please. Oh. It's up to you,
Okay, thank you. Very interesting talk. So can you comment on how would you decide the neighborhood for individual there, or deciding treatment neighborhood?
Yeah. Right, yeah, that's a very practical question when we consider the neighborhood. So in this household interference case, neighborhoods, we can only focus on our spouse. Also, we can also consider our family members. That's one way. So let's in the networks, we assume the first order neighbors have the impact. That's the one way. And the question is how to define your first neighbors. For example, in some studies, they consider the blocks or the clusters. So, for example, the zip code in that in certain area. So all the individuals in this zip code area, they have the interference. That's one way to consider about it. If we have more information about the networks, we can definitely clearly define this neighborhood. Yeah, that's a very practical question, and yeah, we can consider more about it.
Yeah, since you look at things in dynamic treatment regimes, so do you also have sort of like a time-dependent network constructions or weight consider, or you just use a baseline information?
Yeah, that's a very good question. Yeah, so in this project, as we assume it's fixed, not consider the time variant. Yeah, definitely, as I said, that's a promising start. Build on this, more extensions will be considered. Yeah, that's a very good direction we can further investigate.
Okay, thank you.
More questions, please? Oh, good.
Yeah, thanks. Very nice talk. I think my question will expose some of my ignorances. When I see these time-varying problems and people talk about G computation, I kind of get what's going on. And then I see these DTR formulations with blip functions, and I just find those a little bit harder. And so I guess I'm curious, are they completely different methodologies, or does one extend the other? Or what does the Venn diagram look like between G computation and the sorts of techniques you're using? I don't know if that's a well-posed question or not, but.
Okay, yeah, that's also a very good question. So here, this framework is in the treatment regime for the individual's treatment. Actually, so the expectation of outcome here, so in the causal inference, that's the conditional average treatment effect. So we condition some covariance. So we use this kind of estimator essentially to estimate the average conditional treatment effect. For the G computation, that is for the not conditional, it's just for the average treatment effect. That corresponds to the scenario that all the individuals are treated versus all the individuals are not treated. So here, the two different causal estimate, here the method is focused on conditional average treatment effect.
So I'll maybe follow up a little bit, because I thought some of those original early papers on G computation would look at things like start treatment when CD4 count falls below a threshold or something like that. So I'm still trying to understand the boundary between those two technologies.
The boundaries.
Yeah. I mean, I think it's a hard question, but I'm just curious.
Yeah. So so from the theory part and the practical part, we do have a lot of boundaries. So theory part, you can see here, for this regression-based method, also called indirect learning in the some literature. So we construct this outcome model and estimate this blip function, and we make the recommendation for this. So the model misspecification is one problem. It's a real serious problem. So it's hard to model this. Also, for the assumption for the blip part, we assume the linear model. So the truth could be very complicated function. Okay. So one side, it's easy to explain to the physicians. In the practical side, for this, no major confounding assumptions we rely on. That's for the identifiability formula. So that's we need all the confounders. So a lot of the assumptions behind this. Yeah, that's some boundaries.
More questions, please?
Thank you for that talk. It was really, really enjoyable. Question about the network effect in the example of the couples where one is trying to quit and you're looking at the interference between the other, correct? Can the treatment be applied simultaneously to both couples? For example, if both are trying to quit and there's an interaction between them, that would perhaps be accounted for in this model interference?
Yeah, it can cover, yeah. It can cover this scenario, yeah.
No questions more? In this case, yes, so let us thank speaker once more. Good, yes. Thank you very much. Yes.